Welcome. Today we look at triple integrals. I'm sure you have eaten triple integrals before. Let me illustrate this. You have in single variable calculus certainly already computed triple integrals, and I will illustrate this with a shape, a cone. So let's take a cone. So here's the z-axis. And let's just assume we go from 0 to 1. So that's the x, that's the y, and that's the z. And let's just we go from 0 to 1. And let's assume the cone is given by x squared plus y squared. So z is smaller or equal than z squared. And let's also assume that c is between 0 and 1. So it's between here and here, and that means just that the z component is bigger than the r component. Now, what you have done, certainly in single variable calculus, is computed this using slicing it into pieces. I call this the burger method. So what we have is, maybe we have a piece of cheese here. And so what we have here is, this is of height dz, and then we have a piece of maybe tomato. And then we have a piece of a beef. I don't know, I have only purple beef. And then maybe some lattice here. Anyway, what we are doing is, in this burger method, what we are doing is we take a slice like that. Let me just take this, maybe some other tomato here, maybe some other lettuce here, etc. So what we take here is this slice, and so the area here of that slice is given by the radius. This is pi r square, which is just pi z square, because that's r square, right? So when this is equal, that means we have pi z square, and then we have dz. And then what you have done is integrated that up from 0 to 1. So in single variable calculus, what you do is you integrate this, and then you take the area at height z dz. That's what we also call dv. And in this case, this is just from 0 to 1, pi r square pi z square dz, and that's no problem to integrate. That z cubed off, that's pi third. So that's the area here. That's actually, the radius here is 1. That's the area of that whole thing times the height, and then we divide by 3. So what this means, this cone has volume 1/3 of the volume of the cylinder. So that's what you do in single variable calculus. That's called the burger method. What we do in multivariable calculus, we do things differently, which is more flexible often. We use the Fry's method, which matches here. So what we do is we take the same cylinder, and so we have the same base here. So that's the xy plane. And what we do is we reduce it to a double integral. So what we do is we actually integrate here this region here below. We call this region R. So this region R is just the unit disk. Let me just write it down again here. So this R, that's a disk of radius of 1. And we look from above, we see this disk. And now what we do is, like in the bottom to top integration, which we have seen in the double integral, we take a little a rectangle here, and then we go up, start here, where we hit the, maybe it looks like that, we hit here the cone, and then we go up here, and what we see here above is so what we do is we take this kind of what I call French fries. I had not have any French fries and burger since half a year. So because we cannot go to restaurants, so and I don't cook it myself, so that's a fries. And so what we do is we add up all these fries. So if we add up all these fries, what we do is we integrate over that region here. So what we do is we take a double integral over R, and then we take the lower function, which is the lower function here. That's the graph z is equal to the square root. It's actually square root of x squared plus y squared, right? That's what we take. That's the lower part where we enter the cone, and then we go up to 1. Let's see. We go up to 1. So we go, and we can write it like that. And so that's what we usually do now. We say we go from square root of x squared plus y squared up to 1, and dz dx. So that's what we call a triple integral. You see there are 3 integral signs, and that's the right way to look at volume. So we have a triple integral, so we have a cubic centimeters, for example, if you are a physicist. So but the point is that we reduce it to a double integral, and so that fits well. Also, we have an exam coming up where we don't cover triple integrals, but we cover double integrals. So what we can do is, once we integrate that up, we are actually in a double integral setup. So what we have is now we have a double integral problem. Let me just continue here on this side. So what happens is we have now a double integral, and this is something we can forget about triple integrals now. We have a double integral, and what we have learned last time is you have a double integral like that over a circle. It's definitely better to use polar coordinate. So what we have to do is to solve the inner integral here. The inner integral is 1 minus square root of x squared plus y squared. Right, that's the inner integral here. And so we have to integrate from 0 to 2 pi in polar coordinates. Use polar coordinates. And then from 0 to 1. And then we take the function 1 minus r. And then r dr dt. So this r is the integration factor, which we have seen last time. So when we do that, when we integrate that, this gives us r squared half minus r cubed third from 0 to 1. That's 3 minus, that's 1/6. 1/6. This is 1/6, and then we have 2 pi 1/6, which is pi third. And you see we get the same result. We have pi third here, and we have pi third here, with a different method, using fries, using lots of French fries. Okay, let's compute the volume of a sphere using this fries method. There will be a much better method in the next lecture called spherical coordinates, but in this case what we do is we have to identify the region over which we integrate, and that's when you look from above, you see a circle of radius L. So that's important. that we always integrate over the shadow. When we look from above, we integrate over that. That's what we integrate over. And then the French fries here, which we have, they start at the bottom here and they go up to the top. So these are the fries. And so what we do is we just take this double integral, we go from the bottom to the top. Let me just write this down. So the volume is the integral over the region R. Let me just write it down. We don't commit yet on that because we will use other coordinates. Double integral over R. And then we go from the bottom to the top. So this is x squared plus y squared plus c squared is equal to L squared, which means c is equal to square root of c L squared. Just erase this. L squared minus x squared minus y squared. That's what we do, is we start at the bottom, plus minus, right? There's a bottom and a top, minus L squared minus x squared minus y squared to square root of L squared minus x squared minus y squared. And that's the volume. So again, we reduce it to a double integral. What we do is we integrate here this inner integral, we get integral R, that's just 2 times the square root of L squared minus x squared minus y squared dA. And now of course that's much better to do in polar coordinates. So use polar, which is then equal to, from 0 to 2 pi, 0 to L. This is 2 times the square root of L squared minus R squared dr dt. Now we forgot something, and I hope you see what we forgot. I forgot it by purpose. So what we forgot is the R factor. And this R factor actually saves us when we want to compute this. So this can now be computed because we have essentially the 2R here. So that's the integral from 0 to 2 pi. And then we have L squared minus R squared to the power 3/2. And then with a minus sign from 0 to L. When you take L, we get 0. When we get 0, we get L to the cubed. So this is 0 to 2 pi L cubed times 2/3 d theta. And that multiplies by 2 pi. So this is pi, 4 pi. Just write that nicely because that's a very important formula. 4 pi L cubed third. And that's Archimedes. Archimedes, we see here the story. I recorded that in a game, Assassin's Creed. So we have this beautiful formula which Archimedes has done. The next example has also been done by Archimedes. It's called the hoof. So the region, we want to compute the volume of the region. Volume of this. What is the volume of that? So that's a little bit cryptic. We have first to figure out what is actually going on. It helps if we just draw it from above. So what happens if y is bigger than z, so z is sandwiched between 0 and y. So the function y is coming up like that. So this means we have only this part, right, which really matters here. But then we have also x squared plus y squared smaller than 1. So what we actually have is our region, is this region here. That's the region which we integrate over. Let me try to draw this region here. A little bit tough. In space. And then we have the function z is equal to z is equal to y, which is the roof. So let's just see what we actually have, whether we can draw that. It's a little bit challenging here. So what we have is we have the function which. So how does that look like? Maybe it looks like this. So this is kind of, if you look at it from the side, it might look like that. It's a little bit like a hoof. I cannot draw it well, so it's always hard to draw things in space. But you can imagine it here. Let me just show you that here. So you can imagine it better like that. So this is the XY plane, this is the Z, and this is Y is equal to Z, which comes up like that. So it's everything below that tablet and above that green region. So what we have to do is when we use the Fry's method, we go from the bottom up. So this is kind of the hoof. It's a little bit like that. Maybe if I draw it from the side like that, maybe it's better to see it like that. Oh, that's better. So that's the top part, and then the bottom part is the green part on the bottom, right? That's below. Can you see it? It's the hoof. It's what happens if you take a cylinder and you cut it like that. It's kind of, or something, if you cut a tree and you cut like that and you cut like that, you get such a piece. It's called the hoof. We integrate from 0 to pi d theta. R goes from 0 to 1, because that's the thing, the radius goes from 0 to 1. And now we have a volume. So what we do is we integrate now from the bottom to the top. And so this is the integral from 0 to y. But y is equal to r sinus theta. This is r sin theta. Okay, I made here a computation. We go up to y is equal to r sin theta. That was this, we go up from here. But I made a mistake here. I just took 1, and then I forgot here something important. And the important thing which we forgot is, so this is dz. What we forgot is the r factor, because we go into polar coordinates. So this is times r. Now we get, with respect to dz, we get r squared sine theta. So that is equal to, just continue here. So this is equal to integral from 0 to 2 pi, and then we get the integral from 0 to 1. The most inner integral gives us r squared sinus theta dr d theta. Now we can compute this integral here, which is the integral from 0 to 2 pi, and then we get r cubed third, which is sinus theta third d theta, and then we have times 2 pi. So this is times 2, because when we integrate sinus theta, we get the minus cosine theta third from 0 to pi, not 2 pi. 0 to 2 pi would give you 0. So I just copied that wrong here. 0 to pi, integrate from 0 to pi, and that's equal to 2/3. So Archimedes didn't have calculus at his disposal as we have, especially not multivariable calculus, but he did it in a clever way. He computed the volume of a sphere. Let me just show you how. So we have here, let's just take the half sphere instead of the sphere. So this is a half sphere. So what Archimedes did, he took the half sphere and he compared it with a cone, which we have just seen before. So the height is the same, and the cone also has a cylinder here. Let's described. And so here the radius is 1, the radius is 1, and this is the z-axis here. So here's the z-axis. And what Archimedes did, he compared, he took the burger method. So he sliced this up here. Let's assume this is a piece of cheese here. And he knew the formula for the circle. This is this piece here as r. This radius is just the square root of 1 minus c squared. So this is c. He knew Pythagoras, of course, and that's 1. So that's a right angle here. So this is square root of 1 minus square root of 1 minus z squared. So the area here is pi square root of 1 minus c squared squared, which is pi times 1 minus c squared. So that's the area of that slice, and that's the volume is then just when we multiply the dv is then just pi 1 minus c squared dz. So that's the volume of that slice. Now, what we can do here on the other side, we can also look at the little volume here. But what we do is we take this slice of the entire cylinder, and what we do is we cut out the inner part. We cut out what is in the cone. So what we end up is here that ring. So that ring, let's compute the area of that ring. So here this is z, we have seen that. This is z, that's also z. And so that's what we cut out is pi z squared. The whole thing is pi, so dA, so A of z is equal to pi minus pi z squared. And so the dV, this volume of that ring is also pi minus pi z squared, the whole thing times dz. And so this is the volume of that ring slice. And so what Archimedes realized is that these are the same. Right? This is the same volume than this. So when you add up, you don't have to integrate or anything. When you add it up, you just know that the area at the volume is just the volume of the complement. So the volume of the sphere is the volume of the cylinder minus the volume of the cone. And we have just computed the volume of the cone, right? That's pi times 1 minus the volume of the cone was 1/3 minus pi third. That's 2 pi third. But it's the half sphere. That was not the whole sphere, that was just the half hemisphere. So the volume of the sphere (4 pi third), and then we can also multiply with the radius L cubed. And that's the end of the Archimedes saga